So Faraday's law shows up in a fairly interesting way just in everyday application. In all of your homes, you probably have some GFI circuits, and a GFI circuit can be explained based on the principles of Faraday's law. So here's a picture, obviously not drawn to scale, of some guy holding a drill, but he's got to plug this drill in, right? So let's draw the cord. So some cord comes out of the drill, and then the plug might look like what? Got these two prongs, and they're going to go into the receptacle. Fine. Let's take a closer look at this. So that cord that plugs into the drill, it really isn't just one wire. There's two wires. There's a wire that goes in and leads to, it's really just a motor inside the drill, and then the current runs through the motor, and then the wire comes back and forms a complete circuit. So here we've zoomed in on that image. This is the bottom segment of the handle of the drill. And so when you plug this into the outlet, one of the wires plugs into, we'll call it the hot, and then the other wire plugs into the neutral. And now you've got a complete circuit and everything should be fine, except this could happen. You could have a case where the wire that's supposed to lead current to the motor comes loose and touches the case of the wire. And of course your hand is also touching the case of the wire. So what would happen is now this current, instead of making it into the motor, would flow into the case. It would travel around the case and then ultimately through your body and into the ground. And that wouldn't be a good experience for anybody involved. So the protection comes from the third prong in any appliance, especially ones that are designed to draw large amounts of current. So here's an improvement on the design. We add a third wire, and of course you guys know that's called the ground wire. So that one bundle of wires, all wrapped in one plastic sheath, really contained three wires. And this wire goes into the ground. The purple wire where current is going to the motor, we say, is plugged into the hot, and then the red one is plugged into neutral. And the red one should have the exact same amount of current coming back as the purple wire has current going inward, right? The return current and the incoming current should be equal. After all that happens is the current flows around in the armature wire in the motor, but there shouldn't be any loss of current. Okay, so what happens now if the wire comes loose in this case? So if this wire ends up touching the case of the drill and your hand is also touching the case, then current is going to flow around the case. And then here's the thing, it doesn't have to flow through your body. That current can now take this path around the case, and then it can go into the ground wire. Because here's where the ground wire eventually goes. It connects from this outlet to this outlet's ground wire. And then that one connects to this outlet's ground wire. And on they go, and they're all wired together. But ultimately, all these wires just go into, typically they'll go into a water pipe. And then that water pipe continues below ground into wet soil, and there's a path now for electricity to flow instead of through your body, through this wire and through this wire and through this wire and into some metal and into the ground. And I don't know, maybe your body is in parallel, and so maybe a tiny amount, just a little bit of electric current will also flow through your body, and so there's a path number 1 to ground and a path number 2. Number 1 being just bare copper wire that leads to a water pipe, and all of that is a very small resistance. And then there's a path number 2, that's your body, which represents a larger resistance. And so if you were touching an appliance where the internal wires came loose, you might feel a tiny tingle because the amount of current flowing through your body would still be less than that 5 to 10 milliamp value that causes a little sensation of tingling your body, but doesn't, it isn't a fatal amount of electric current. Now, there's an improvement on this design. It's called a GFI circuit, a ground fault interrupter circuit. And if your appliance were to have some failure of the internal wiring, in that case, there'd be absolutely no current that would flow through your body. In fact, well, I'll show you how the GFI circuit is an improvement on a ground wire. So it's something like this. Your appliance, maybe it's a blender in this case, right? There, you got your Vitamix plugged in here. All your little switches and buttons. And of course there's some cord that comes out of here. And it seems like it's just one cord that gets plugged in. But in the exact same way, it's right, a wire from the hot, and that goes to the motor that controls the part that makes the blender spin. And then you've got the return current. That goes to the neutral, and there's still a ground wire as well, although not really necessary in one of these GFIs. So this is, now I'll draw a picture behind the wall of your house. Okay, so the outlet's in the wall, and then back here, behind the wall, these wires continue onward. So the red wire continues here, the purple wire continues here, so there should be an incoming current going this way, and there should be a return current coming back this way, and those two amounts of current better be equal, otherwise there's been a loss of current, and that implies that some wiring has come loose. And so here's how the GFI takes care of that. There's a loop of something that has a pretty high relative permeability or susceptibility. So this could be like an iron ring. So let's see, are there any magnetic field lines in this iron ring? Well, if you point your thumb in the direction of this current and you wrap your fingers around to try to figure out the direction, oh, that's a bad picture of a hand. Anyway, you get the idea. Yeah, there's magnetic field lines that are going, let's see, as an eyeball were to look from this direction, I guess that eyeball would say there's some counterclockwise magnetic field lines due to the incoming current. But then again, you have the return current, and that would make magnetic field lines in this iron ring that this eyeball would view as clockwise magnetic field lines. And so in fact, the net magnetic field in this iron ring should be equal to 0. Now we add one more little element to this. There's a coil of wire wound around a portion of that iron ring. And then that wire goes off to a control unit. So here's the thing, as long as your incoming current and your return current are equal, the net magnetic field in the iron is 0, and then there's no current at all in this blue coil right here. But what if all of a sudden this return current disappeared because one of the wires came loose in your Vitamix and touched the case? Then that sudden loss of return current would mean the net magnetic field is not 0, right? There wouldn't be the clockwise magnetic field lines in the iron ring. There'd only be the counterclockwise magnetic field lines in this loop. And so we'd go from a case of having no magnetism to having some magnetism, and that magnetism passes through the windings of this sensing coil. It's like wrapping a solenoid around this iron ring. And so that sudden change in flux makes a current. And then that induced current goes off to a circuit breaker that suddenly shuts everything off. So at the very instant the return current goes away, there's a shutoff that takes place. And so even if you were touching the Vitamix at that point, well, that's a funny looking person, huh? There'd be no current flowing through your body because that current would just suddenly go away thanks to the circuit breaker. So, pretty clever design, these GFIs.